Hello. New slides. So my name is Rosalyn Moran, and for the next 14 minutes and 57 seconds, I'm going to go through a didactic walkthrough of active inference, or the free energy principle, and how neuromodulators might be well placed to support neurobiologically the implementation of this quite formal theory of the brain. So to contextualize this research, we know that there really isn't any computational psychiatric disorder that doesn't affect or have some link to abnormalities in neuromodulatory systems, from serotonin and dopamine to noradrenaline, acetylcholine. But what we'd like to do in a computational psychiatry, and this is text taken from a recent book by Josh Gordon on computational psychiatry, is propose a sort of taxonomy where we outline what we're talking about, something like an effective or functional connection. In modeling the brain, what we might talk about are normative models, where we're trying to describe the goals or what the brain is doing, and also process models about how we might do this. And so examples that you might have heard of are reward maximization being a normative principle, which might be instantiated through dopaminergic midbrain firing. And what I'm going to spend this talk on is looking at the free energy principle, where we're trying to minimize surprise as a formal goal, and how we may do that in different contexts via predictive coding or variational message passing, and the crucial role that neuromodulators, particularly acetylcholine and noradrenaline, have in this process. So the free energy principle is really the idea that you, in your brain, your synapses, particularly your synaptic connections, as well as your neuromodulatory tone, try and become a model of your world. So if you imagine that you didn't come to Rome this past week, but instead you went to New York City and you're walking down Fifth Avenue, the free energy principle has an instantiation for continuous state space models, where we might be in a dynamic environment that has exotic noise and hierarchies, and we're trying to build a model so that we can make predictions and minimize our surprise or free energy and, say, predict the speed of a taxi. And this normative goal, minimizing free energy, could be accomplished through predictive coding. Similarly, if we wanted to be minimizing our surprise, we'll have to try and make some discrete decisions. So, for example, the decision to take a taxi or a subway. And so what I'm going to show you in this talk is how a representation of the world as a partially observable Markov decision process can also be useful in terms of understanding potentially the role of noradrenaline, where again one might try and minimize free energy as a normative goal using variational message passing. So what is free energy? So those of you who do machine learning and variational autoencoders might have heard of ELBO, or the evidence lower bound. So the free energy is really a bound on surprisal. Here I've written the negative free energy. So it's basically how likely are you to occupy or to see data that you expect, or a log probability of y. And it's capped because by this non-negative term, which is a KL divergence between stuff I think my brain sees in the world Q and stuff that really is in the world P. So it's just a statistical quantity that describes a procedure or a sort of measurable metric that allows us to make inferences so that our brain is a good representation of the world around us. So, for example, on the left here, we may have a large KL divergence where our free energy hasn't quite bounded to our model evidence, and so we're estimating that the speed of a taxi down Fifth Avenue is 100 miles an hour. But once we get a better model and try and do good perception and close that bound, we may have a better real estimate of the real statistics of the world and a decent estimate of the speed of the taxi. So essentially, minimizing free energy is trying to create a scenario where the probabilities of things happening in the world, P, are closely related to the probabilities instantiated by the synaptic connections and neural activity, Q. But in calculating free energy, and this is the last busy equation, we can rewrite it and say that it's basically like an Occam's razor. So we want to be as accurate as possible while keeping complexity to a minimum, and we can do a gradient ascent. And it's these pieces, so the little mechanics of the gradient descent, that might have some role for neuromodulation in different parts of cortical connectivity. So looking at maximizing free energy, we'll start at looking at these sensory hierarchies in this continuous domain and a putative role for acetylcholine, coming back to this gain control idea. And we know that acetylcholine has been proposed by several people in the literature. So new ideas on neuromodulation are that it can be quite selective, as you saw in Mac's slides. So rather than a large volume conduction, we can have particular controllers from frontal cortex activating particular cholinergic cells that will be selectively influencing sensory cortices. Michael Hasselmo has basketed acetylcholine into particularly in the hippocampus, as changing you from a readout mode to a read-in mode. And Angela Yu and Peter Diane have proposed that acetylcholine works to signal expected uncertainty. So when you know the environment is going to give you low probability events. Okay, so to break down this predictive code and how acetylcholine might work, the idea is that you have predictions potentially from deep layers that go back down the cortical hierarchy. So we may have some prediction like I'm in New York City, and so there will be yellow taxis, and it is a yellow taxi, might be signaled to our ventral stream, whereas our dorsal stream might predict that a taxi is in a particular place. And this forms part of the free energy and the gradient ascent on free energy that we need to potentially do this computation. Prediction errors emerge, so this is the predictive coding idea. So an efficient way to understand our environment would be to do this gradient descent. So we try and understand the world by instantiating prediction errors, or the difference between what we predicted and what we saw. And this may be what are encoded in these forward connections that tend to come more from the superficial layers 2 and 3. And so our prediction errors will travel up our brain until we have a sufficient prediction, or we recognize that there might be no taxis. Then the role for precision or gain control is this scaling term here, which is an inverse covariance matrix or a precision matrix, which basically allows us to control which prediction errors we may pay attention to. And this is the putative role of acetylcholine and other neuromodulators under the free energy principle. And so it allows us to direct attention potentially through these frontal fields. So if you wanted to get a taxi, you wanted to observe a yellow taxi, then maybe you will boost the prediction error in the ventral stream to identify a yellow taxi. Whereas if you wanted to just walk safely across the road, then you may want to boost your prediction errors in the dorsal stream and make sure that the taxi is out of your way. So in a very simple environment, in an auditory world, we looked at this with a cholinergic manipulation using galantamine, which is a cholinesterase inhibitor. So it would boost acetylcholine in human participants undergoing EEG. And what we did was actually run this free energy gradient descent and look at the so-called superficial cells and see how they generated a model-based EEG response and a mismatch negativity response. And we saw differences in the mismatch negativity in that under galantamine, our simulations showed a much bigger MMN and a mismatch negativity that hung around for a little longer. So you're sort of keep getting surprised even though the tone had changed. And in terms of looking at this in the EEG, we were able to replicate using the MMN, a central channel, that this MMN response was indeed observed in our empirical data at the scalp level. And we brought that one further using dynamic causal models and tested whether the EEG signal and its modulation by galantamine could be ascribed to deeper superficial layers in either primary, secondary, or frontal cortices, or whether they were on connections directly. And in line with the theoretical ideas, what we found was that a model where the superficial cells in primary auditory cortex boosted the prediction error through A1 was the best model of our data. So that was a sort of continuous world, a simple sort of trying to estimate almost like a Bayesian filter. And what we've looked at more recently was noradrenaline in a more discrete decision-making capacity. So this is also the idea of trying to minimize your surprise into the future, but rather doing it in this discrete domain, we would be looking at noradrenaline. So this is things like making plans to play chess or trying to plan the Brexit future of the UK. And again, in noradrenaline literature and the theories and formal ideas on what it does, Sebastian Boré and Susan Sarah have this idea of network reset. An idea from Aston Jones and Cohn, supported by data from macaques, is that it controls the explore-exploit phenomenon that you see in decision-making. And in this you and Diane concept, it's a sort of unexpected uncertainty or a contingency change that one might be signaling through LC firing. And so this is kind of a busy slide, but the idea is that you can plan into the future your potential free energy, and how if you make a series of decisions here, pi, you can reduce the so-called cost. So how likely are you to get to your goals, P0, and also reduce uncertainty. So you want to get to your goals and be sure that you're going to reach them. So you can get to your prior while you get to know the place. And there's some rearrangements that give you interesting ideas on epistemic value, so how you seek out curiosity seeking under these sort of rigid formal ideas. And here we move away from the sensory cortices into the basal ganglia and frontal cortices as a putative neurobiological implementation through message passing in hippocampus, the basal ganglia, and the frontal cortices. And so here, the sort of scaffold that we think the world is working on is this general POMDP. So this is just a little cartoon for those of you who are enjoying or not the Brexit negotiations. So we may have three outcomes: a soft Brexit, a remain, or a hard Brexit. And so to instantiate that into a POMDP, we have at the lower level these hidden states. So politicians may say something and mean something else, so they may be pragmatists or Eurosceptic. And if the Prime Minister decides to make a certain action, like assemble business executives, then we may have some shift from hidden states to hidden states and a certain outcome. She might decide to have another meeting, maybe with Nigel Farage, and then you might have different outcomes depending on how the states shift. And so under a POMDP, these shifting of states from things that are hidden to outcomes you observe are controlled by these transition matrices and likelihood mappings, the so-called A and B matrices of discrete active inference. And so what we proposed in this recent paper was that these two ways of sort of reducing uncertainty about the world, you could either move into the future in a way that you were certain you would have a certain outcome, or you would try and rebuild your model if it wasn't fit for purpose. Might have something to do with the LC in terms of its sort of general idea of resetting networks or responding to uncertainty. And so what we proposed here was that the driver of LC was a state action prediction error. So suppose I'm in a Tory cabinet meeting and suddenly someone I thought was a Eurosceptic is now a Remainer, then I may have a large state action prediction error based on talking to them. And so this we thought may be reflected by inputs to the LC which cause locus coeruleus firing. And what you can do nicely is you can simulate LC firing over time, over trials, but also within trials as you're trying to plan ahead your next move into the future. So that's coming into the LC in this model. Coming out of the LC is something that allows you to rearrange those contingencies that you thought you knew. So here we have from the LC something like a large state prediction error might increase the attrition rate of existing experience-dependent parameters. So basically just those matrices that you think, if I do A, then I move from state 1 to state 2. Now I'm not so sure that those actions will give me those particular transitions. So we built that into the model, rather like a learning rate that you would see, but embedded into this free energy decision-making into the future. And what we were able to show was that in quite precise terms, we could simulate neuronal firing in a go, no-go task. So we simulated this sort of free energy planning using a rodent-like task where they could go in at a certain queue and get a cookie with some probability and get no reward at another queue. And there was a small cost of moving in our model. And what we found was that we reproduced this classic tonic and phasic firing of the locus coeruleus, where a well-trained agent had this nice phasic response at the activity of a go queue, as you see empirically. And then when we switched the queue contingencies for go and no-go, what we found was this large tonic burst of LC firing that was protracted until it relearned the contingencies here to the right over time. We also did some things like, from the literature, we know that depending on the size of the reward, but also the proportion of go and no-go, you get different sizes of spikes. And at that level of detail, we were able to reproduce those empirical results with this particular model. And then finally, our flexible rebuilding, allowing us via the locus coeruleus inputs into the cortex to rechange that model, led us to have a behavioral optimality that was superior to some fixed learning rate from before. So in conclusion, if we think about a formal theory like the free energy principle, what we might punt is that neuromodulators have a really crucial role in that they are really traffic cops directing predictive codes in the context of sensory channels, and potentially in the context of decision making, we can simulate with high resolution the sort of firing that you might see in an animal during a go-no-go or a foraging task, allowing us for a controlled gain of model rebuilding. So we sort of retain who we were yesterday, but try and update it in an optimal way. So with that, I'll thank you for your attention and thank my colleagues in Bristol and King's and Karlsruhe.